In the circus, they have these motorcyclers that are riding around inside of a spherical cage. They got like multiple motorcyclists in there at the same time, and I don't know how they keep from hitting each other. But I can tell you how they keep from falling down when they're at the top of the cage like this. We can kind of intuitively sense that the faster this guy's going, the more he's going to stick to the inside of the cage when he's at the top. And what that is related to is the centripetal force required to keep him going in a circle. This is also called the radial force. So we're going to give a little r for radial subscript. We've already seen how the equation for the radial force, or the centripetal force, is the mass of whatever's going in a circle times its velocity squared, and that's its tangential velocity. So basically it's speed in whatever direction it's going at the time, divided by the radius of the circle. So here's the reason why faster means you're going to stick to the walls more. You have velocity proportional to the centrifugal force, and that centripetal force comes from the pushing of the inside of the cage against the wheels of the motorcycle. So let's think about a situation where this guy's going really fast around the cage in here. And he is, let's say he's over here, he's coming around, and he is going in a uniform circular motion, so we know he's getting accelerated toward the middle of the circle. Okay, timeout, correction. It's not uniform because he's not going at a constant speed, because gravity accelerates him to go faster when he's at the bottom than when he's at the top. He slows down when he's at the top. So this isn't really uniform circular motion. But anyway, he's accelerating at all times toward the inside, toward the center of the circle. So if he's right here, there's a force that's accelerating him toward the inside of the circle, and that force is applied by the wall to the tire. And he goes a little farther, he comes up here, and there's still a force from the wall on the tire that's accelerating him toward the middle of the circle, that radial centripetal acceleration. And he gets up to the top, and there's still a force from the inside of the wall on the tire that's pushing him toward the middle. But at the top, think about what other force might be pushing him toward the middle of the circle and helping him to centripetally accelerate. Is gravity. There's always a gravitational force on him going downward. So there's his mass times g, his weight. That force is also accelerating him toward the middle of the circle at that point. So when he's going really fast around here, the centripetal force that is accelerating him toward the middle is the sum of these two vectors. So really it's like that much force. That would be like the FR, the centripetal force, the sum of his gravity and the pushing from the inside of the container. But the gravity doesn't help when he's not on the top. By the time he gets over to this side here, gravity's still going down, that force from gravity, and this is perfectly perpendicular to the direction that he needs to have the force act on him to radially accelerate him. So the centripetal force at this point in the circle has to entirely come from the contact between the wall and his tires. So that entire centripetal force vector has to be applied from the wall because gravity isn't helping at this point. And once he gets all the way down to the bottom, then gravity is actually providing a force in the opposite direction. So the force from the inside walls on his tires have to be even greater to counteract the gravitational force. So the force from the bottom of the wall and the tires has to be equal to the centripetal force plus the mg vector of the gravitational force. But anyway, I think it's about time to get to the point here. The point is that we're trying to find the slowest possible velocity that he could be going and not fall off the top of the cage. And that brings us to the trick of how to figure out this problem, which is that at that point where he's going the slowest possible velocity, the centripetal force is exactly equal to the gravitational force. Because if he was going any faster, then there would need to be force applied from the inside of the cage to the tire, in addition to the gravitational force to keep him going in that circle. And if he was going any slower, then the gravitational force would be more than is required to keep him going in the circle. And his circle would suddenly have a smaller radius and he would fall inwards. But anyway, that's the trick here for this problem. To say that his weight, mg, must be equal to the radial force, the centripetal force. And we know that we have an equation for that, which is mv squared over the radius of the circle. And what this equation basically says is, so we're just taking out the fr, and then we notice that there's an m in both terms, so we can divide both sides by m, we can cancel out the m's, and then we can get down to business of solving for v, that velocity. I multiplied both sides by r. I take the square root of both sides to solve for v. I put on our values here. We know that the acceleration of gravity is 9.8 on Earth, and it's given in the problem that the radius of this circle that the motorcycle is going in was 10 meters. And we find our answer, 9.9 meters per second, which is about 22 miles an hour.